Hi, Mark here with My Engineering, and for today's video we're going to be doing an end-to-end workflow on total runout inspections. So total runout inspections, if you're not quite familiar, is very similar to just a regular runout inspection. The difference is you're working in 3D space. So a single runout inspection, you'd be basically doing, if you can imagine, revolving a cylindrical piece, let's say, around its axis, and you have a dial indicator on one spot. As it comes around, you're basically getting a reading of the surface of that object relative to its central axis. Total runout, by contrast, is doing the entire surface. So if you're using 3D scanning data, you're getting up to millions of data points along this surface, and using all of those to generate your inspection data. So for our inspection piece, I'm actually going to be using our little cardboard shipping container here. This is for what we use to ship our tripods. I know it's not going to be perfect, obviously, it's cardboard, but it'll be a good test piece to try and determine what a runout inspection would look like using 3D data. And we're going to be collecting that data using our Scantech TrackScan Sharp today. So the advantage of using the Scantech TrackScan Sharp is that you do not need to put the tracking targets on the object itself. Those tracking targets are incorporated on the scanning head. So you don't need to do very much prep time, if any, on the object that you're scanning in order to generate a highly accurate 3D point cloud. As you see here, in just a couple of minutes, we're able to generate a model that we're going to use for our total runout inspection. All right, so now we've brought our piece into Inometrics Polyworks Inspector, and so that's what we're looking at here. So this is our meshed file that we just scanned. And first step that we need to do is create a data cylinder on the object surface. So we're going to use our cylinder selection tool, and we're going to make sure that our detection zone is set to multiple, because we're going to assume that this is going to be a little bit less than perfect. So we're going to have to probably click on it a few times to gather enough data points for it to create the cylinder. And I'm going to show you what I mean by that. I'm going to click on it once. It creates sort of a best fit cylinder on what it thinks is kind of the same area. I'm going to click again over here. Now you can see the green area over the object. That is the data points that it is actually using to create the cylinder. And you can see there's a big area at the base of the cylinder that it's not using. So we're going to click on that area as well. Okay, so now we just spin our piece around and make sure that we have good coverage. And you can see as we spin it around, there's a whole area here that isn't being used. I'm going to select one more time up here and see if that kind of fills it in a little bit better. What that probably means is that it's a little bit ovaled or egg-shaped, something like that, where that part of the data doesn't fit what it thinks is part of the cylinder. So we want to make sure that that data is actually included. Now this is looking pretty good. So I'm going to accept this. We can close this tool. Next thing we're going to do is we're going to extract a datum axis from the cylinder. We want to create a line. We're going to call it datum feature A from cylinder axis. We can go ahead and create that and close. So now in our object tree, we have a cylinder and a datum line A. On the cylinder, if we go down on the bottom of our screen is our geometry controls. But what we want to do is we want to add a GD&T control. So on the very right side of our screen, there's a little menu that we can open, and we want to select total runout. And so it gives us a little menu for setting up our total runout. Let's say we want to have a tolerance zone of 4 millimeters. Let's see if that works, relative to datum A. So we can see the results as soon as we create that data object. And in the bottom of our screen here, you can see there's a fail on the right-hand side. So we set a tolerance zone of 4 millimeters, and it measured 5.851. So this is not within the tolerance that we set for this particular inspection. And if we wanted to, we can go ahead and create a report for exactly just total runout, if that's the only feature that we want to inspect on this object today. So something that I really like of Inometrics Polyworks is how it presents your inspection data in report form. In this case, I decided to do a little bit of a color map snapshot above our inspection data. I'm going to come back to that in a moment. But for a control view, so we have only one inspection item that we input for cylinder 1. Our control was a total runout with tolerance of 4 relative to datum A. It'll give you the measured, which in this case was 5.851, our tolerance, our deviation, and then the test. So if it is a fail, it'll be presented in red. It's very easy, it stands out, so you can quickly see any items that are out of tolerance. And then of course it'll tell you how far out of tolerance it is. So in this case, 1.851. And then going back to the color map analysis, I really like this feature in Polyworks because of how easy it presents the data, especially for things like runout or cylindricity, or if you have a CAD model and you want to compare like a cast part or a 3D printed part to see how close it resembles what a perfect model should be. In this case, as we rotate it around, you can see very clearly that it is a little bit ovaled, not something that I would be unexpected of a cardboard part, but it presents the data very, very cleanly for us. So now you've seen how easy it is to do a total runout inspection, but you might still be wondering, why would I want to move to a total runout inspection instead of sticking with the standard runout inspection with some kind of a mechanical means of measurement that you may be already used to? The answer is quite simple. If we were to look at our cardboard tube again here, if I was to take a two-dimensional cross-section of this piece and get one circle of data, that would be representative of a runout inspection. That sample might actually be well within tolerance, but if you're to take that same sample here, it might be outside of tolerance, and over here, completely out to lunch. If you do a total runout inspection, you're getting the entire surface of the data that you scan to make your determination whether the part is within tolerance or not. So it's a much more accurate, much more robust inspection. When you pair that with something like a Scantech TrackScan Sharp, the accuracy of your data could be up to 1/1000th of an inch accurate and possibly spread across millions of data points. Well, that's all for today. I hope you guys found that video helpful. If there's anything else that you'd like to see, you can always reach out to us, support@myeng.ca, or leave a comment in the comment section below. Thank you for watching, and we'll see you in the next video.